Hello, welcome to another module in this massive open online course. So, today in this module we are going to look at a different modulation scheme, that is M-ary PSK or M-ary phase shift keying, similar to M-ary QAM, which is quadrature amplitude modulation and has M symbols. M-ary PSK or phase shift keying has M symbols and it is a phase shift keying based digital modulation scheme. Okay. But before we proceed further, just want to make a minor correction in the overall probability of symbol error derived for M-ary QAM last time. There has to be a factor of 2. So, this twice, as we have seen, the overall probability of error is twice the probability of error, approximately twice the probability of error for the constituent QAM. So, for the constituent M-ary PAM, so this has to be 4. Okay, because the probability of error for the constituent PAM is a factor of 2. So, this is twice that, it will have a factor of 4. This is 4. Okay, this is a factor of 4. This is twice the probability of, so probability error of PAM or P QAM is approximately twice P as shown below. Okay. Anyway, so let us move on to our modulation scheme under consideration, which is yet another modulation scheme, a digital modulation scheme, which is termed as M-ary phase that is your M-ary PSK. This is another digital modulation scheme, and again this also generalizes the concept of binary phase shift keying, which has 2 phases, generalizes the concept of binary phase shift keying BPSK binary phase shift keying or BPSK, which has two phases. Okay. And it generalizes to M-ary phase shift keying. In M-ary phase shift keying, basically there are M phases. So, in binary phase shift keying there are 2 phases, right, plus or minus a, that is 0, 180 degrees. So, if you look at binary phase shift keying, there are only 2 phases, which are 0, 180 degrees. So, M-ary phase shift keying generalizes this concept of binary phase shift keying and allows for M phases, that is symbol can have one of M phases, and this has M symbols, M possible symbols or M possible symbols in the constellation, and therefore once again similar to M-ary QAM, one can communicate log M to the base 2 bits per symbol. Okay. So, there are M possible phases. Okay. M-ary PSK impossible symbols implies the constellation has m symbols, implies we have log m to the base 2 bits per symbol. We can communicate log m to the base 2 bits per symbol, and the m possible phases in M-ary PSK, the m possible phases are 0, 2 pi by m, 4 pi by m, and so on so forth until 2 pi m minus 1 by m. So, these are your m these are the m possible phases. Okay, these are the m possible phases, and so basically the the ith phase, you can write it as 2 pi I by m, where 0 less than or equal to I less than or equal to m minus 1. Okay. So, we are taking 2 pi, okay, 2 pi, remember 2 pi corresponds to 360 degrees, and we are dividing it into m possible phases. Okay. So, basically what we are doing is dividing 2 pi into m possible phases. Dividing 2 pi into m possible phases. Now, of course, m equal to 2, again you see if m is equal to 2, for m equal to 2 the phases are 0, comma 2 pi I, where I is equal to divided by m, 2 pi divided by 2 equal to pi. So, phases are 0, comma pi for m equal to 2, which means it reduces to binary phase shift keying. So, if you consider m equal to 2, the phases are again 0 and pi, that is 0 and 180 degrees. So, for m equal to 2, this reduces to binary phase shift keying, alright, and in general you can have any m, alright. So, that is M-ary phase shift keying. So, we are generalizing binary phase shift keying, which corresponds to m equal to 2 phases, to M-ary phase shift keying, which contains one of m possible phases, that is symbols can take one of m possible phases. Okay, that is the whole idea. So, this reduces to binary phase shift keying. The idea is reduces to BPSK for m is equal to 2. Okay. Now, let us look at the constellation diagram. As I have said, we are taking a phase of 2 pi, we are taking a phase, remember phase of 2 pi corresponds to 360 degrees. So, you can represent it using a circle, you can represent it using a circle. Okay. Now, the first symbol is at phase 0, okay. Second symbol is at phase 2 pi by m, this is let us say 2 pi by m. Third symbol is at phase, right, the phase difference between the symbols. So, third symbol is at phase 4 pi by m, this is phase 4 pi by m, and so on. and the radius of the circle. So, radius of circle equals A. Okay. The radius, so these constellation points, this is a constellation. So, this is another constellation point, this is the 0 constellation point corresponding to I equal to 0 constellation. So, this corresponds to I equal to 0, this corresponds to I equal to 1, this corresponds to I equal to 2, right. So, the ith point where I lies between 0 and m minus 1 is at a phase 2 pi I over m, 2 pi I over m, alright, on the circle of radius A. I can take values from 0 to m minus 1. Therefore, there are total of m points. Each is phase shifted from the previous one by 2 pi by m. So, we are taking the phase, total phase of 2 pi 360 degrees and dividing it into m phases. Okay. And therefore, now if you look at the ith point, okay, if you look at the ith point corresponding to phase. So, if you look at the ith point, two pi I over m, radius is A. So, if you look at this, the x coordinate is going to be A cosine 2 pi I over m, and if you look at the y coordinate, that is going to be A sine 2 pi I by m. So, this can be represented as symbols, two symbols, one is the x coordinate. So, each constellation point, okay, so this is constellation point I. So, this can be represented as a combination of two symbols. A1 is the x coordinate, which is A cosine 2 pi I divided by m. A2 equals A sine 2 pi I divided by m. So, it is a combination of two coordinates, alright, A1 and A2, alright. Each correspond to, now you can say that each of these corresponds to basically each of these is transmitted along, right. We have two symbols, right, similar to QAM, it is a combination of two symbols, each is transmitted along an orthonormal basis function of the signal space. So, the net transmitted waveform xt can be xt equals A1. So, this is similar to QAM. Okay. So, net waveform, so this is your transmitted waveform, okay, where A1 belongs to the set A cosine, or let us use the index k, A cosine 2 pi k by m. I am simply changing the index to k equal to 0 1 up to m minus 1, and A1 or A2 element belongs to A sine 2 pi k by m, k equal to 0 1 up to m minus 1. Okay. So, we are transmitting, and of course, as we have seen before, P1t and P2t these are orthonormal basis functions for the signal space. These are the orthonormal basis functions for the of the signal space. For instance, we have said that is P1t equals, well, again unit norm, that is unit energy, square root of 2 over t cosine 2 pi FCT P2t is square root of 2 over t sine 2 pi FCT, where 0 less than equal to t less than equal to capital T, the symbol duration, and t, correct, t equals k over Fc, or basically contains an integer number of cycles, okay. So, that is basically what we have seen before also, okay. And the kth symbol, remember we have said kth symbol is A, well, times cosine 2 pi k by m, A times k2. So, the kth symbol, or basically the kth constellation point, is A cosine 2 pi k by m, A sine 2 pi k by m, okay. So, this is your kth constellation point. This is the kth constellation point, and now if you look at, and now if you look at the average energy, average symbol energy, that is equal to expected value of, well, expected value of, you can say average energy of the waveform, expected value of xt square, expected value of, or expected, or energy of at square, or expected value of, you can write this as expected value of integral minus infinity to infinity, just be a bit more elaborate, minus infinity to infinity x square t dt, which is equal to, well, let us write it this way, minus infinity to infinity A1 P1 t plus A2 P2 t whole square dt, okay, well, which is equal to the expected value of minus infinity to infinity A1 square P1 square t dt plus A2 square integral minus infinity to infinity P2 square t dt plus twice A1 A2 integral minus infinity to infinity P1 t P2 t dt. Of course, this is nothing but energy of pulse EP, energy of pulse EP, and this thing is nothing but integral minus infinity to infinity P2 t dt. This is 0. This is nothing but the inner product of P1 t P2 t. Pulses are orthogonal. Since pulses are orthogonal, in fact they are orthonormal, so this is equal to expected value of, and you will observe something very interesting over here. This is equal to expected value of A naught square E p plus A 1 square E p. Well, E p equal to 1. So, this is equal to expected value, that energy of the pulse is equal to 1 A naught square plus A 1 square E p equal to 1, that is we are considering a unit energy pulse. Okay. Now, this is equal to, remember A naught, I am sorry, this is not A naught, rather A 1 square plus A 2 square. Okay. And remember A 1 is A cosine 2 pi k by m whole square plus A sin 2 pi k by m whole square, which is equal to, of course, A square. A is a constant, expected value of cosine square 2 pi k by m plus sine square 2 pi k by m. This is of course 1. So, this is equal to A square. So, basically what we have is, if you look at this, the expected value, average symbol energy or expected value of x t square or expected value of x square equals A square, setting the symbol energy equal to E s, we have A square equal to E s, which implies A is equal to square root of E s. So, the radius of this circle, the radius of the circle of the constellation. So, if you look at the constellation, the circle of the constellation, correct, the constellation is a circle, the radius of that circle is square root of E s. And in fact, all symbols have, unlike QAM or PAM, where the average energy is E s, here not only the average energy, but actually the energy of each symbol, if you observe it, because the radius is constant, the energy of each symbol is E s. Okay. So, that is something interesting about the M-ary. So, if you look at the M-ary, so A equal to square root of E s, that is radius of circle, and you can observe that each point has each constellation point, unlike PAM, each constellation point has not only average energy, but each constellation point actually has energy E s. Okay. So, that is basically your M-ary PSK constellation. So, M-ary PSK constellation consists of m points arranged around a circle of radius square root of E s, and each constellation point differs from the previous one by a phase shift of 2 pi by m. And the ith point or the kth point is given as A or square root of E s. Now, we can say, since A is square root of E s, this is square root of E s cosine 2 pi k over m, and A, it is a combination of two basically coordinates, that is A 1, which is square root of E s cosine 2 pi k over m, and A 2, which is square root of E s cosine 2 pi k over m. it. So, we will stop here and look at the receiver design, the detection and also the ensuing probability of error and other aspects in the subsequent modules. Thank you very much.